What? I need to pull the screen down. Okay, so first for Wednesday, there is a video and an online quiz to watch. That material I don't think will be on Friday's exam, but in order for us to keep pace, that'll be there. It's already there, actually. We'll use Wednesday for any questions. If you don't have questions, then I guess we'll go over that stuff. But today's material will be the end for the exam on Friday. Yeah.
So for the video today, you started going into the naming of the clock side.
Yeah, I don't know that there'll be.
Okay.
Well, I don't know that there'll be any naming on the exam, but the reactions would certainly be legitimate because they're not that much different than what we've done. So reactions, yes. Naming, probably not. Sarah?
As far as reactions go, would it be a lot of stuff, like which reagent goes from here, or if you want mechanisms as well?
So if you look at the older exams, the only thing that's missing from the old exam number ones, the recent exam number ones, is triple bonds. Because normally we finish triple bonds up in the first semester. So there will be triple bond reactions that aren't on the older exams. So if you want to see triple bond reactions, well, you're kind of stuck because they would be on the final exam from last semester, which nobody has but me. So you'll just have to know your triple bond reactions. You can go back and look at the homework, some of the practice problems. Other than that, you'll see that it's pretty much the same format as last semester. So I'll start with some mechanisms. I'll ask you to write products of reactions, and then I may have a couple of schemes where you have to give me reagents. But it's not going to be, the whole thing's not going to be reagents. It'll be split like maybe like a third maybe. A third, give me another third to play with. So if you look at the newer, older exams that are online, that'll give you kind of the template. With maybe an occasional, with some other question about, explaining something. Anything else about Friday's exam? So you're going to need to know your reagents, but you'll also need to be able to write products. And we have quite a few reactions that we've already done this semester. Okay, any questions about today?
Could you explain what happens after you cut out a toxic chloride and then you react with any?
Okay, so if I take an alcohol, and specifically this was the one from the homework. If I take my tosyl chloride and I react it with my alcohol, what am I going to get? I'm going to get a tosylate ester. And then once I get that tosylate ester, I can do a number of things with it. Primarily, I can do SN1, I can do SN2 or E2. Right? I can substitute and kick off the tosylate ester, or I could use a base, and do elimination. So either SN2 or E2. So the question is, if I react this with NaBH4, what's going to happen? So my first question is, what's NaBH4? What? Is the source of H minus, right? So then the question is, what's the H minus going to do with this molecule? So it's going to do what mechanism? So it's going to do an SN2. It's going to come in, kick off the leaving group, and I will basically reduce the alcohol. So I'd buy that except for one problem. And I will accept this. But what kind of tosylate ester do I have? Primary, secondary, or tertiary? It's tertiary. So can that undergo SN2? No. So I'll accept that answer for this time. But really looking at that can't undergo SN2 because it's tertiary. So what I should do instead is I should think about an E2 mechanism. And so then I have to, there's my alpha carbon, there's a beta carbon, there's a beta carbon, there's a beta carbon. So then I have to think about, okay, which beta hydrogen is going to be removed with an H minus? Is it going to be one of the beta hydrogens that are on the ring, or is it going to be a beta hydrogen that's on the methyl group that's outside of the ring? So my H minus, if it decides to do E2, is it going to remove HA? Or is it going to remove HB? And we might as well make this somewhat interactive. So if you have your card, so if you got your card with you, A or B or C would be both equally. So your choice is it going to remove HA, is it going to remove HB, or is it going to remove the two of them equally, which will be C? Okay, so those are your choices. Okay, I've got a whole plethora of answers. 8 A's, 9 B's, and 5 C's, and a D. I don't know what the D stands for. So maybe we need to discuss this for a moment. So take a moment, take a minute, discuss with a neighbor what you got, and then we'll revote and see. Because right now we're kind of split all the way across the board. A, B, and C. So I'll give you a minute. Okay, we ready to revote? Let's go ahead and revote. Okay, A, B, or both equally for C. All right, it moved to B at 19. 19 people voting B. So why did it move to B? Somebody want to give me their logic? Brian?
If you draw the two possibilities and they eliminate them, so the one possibility is double bond in the ring, and that would be if you lose. So the left one would be option A, and the right one would be option B.
Okay.
And if you count the number of hydrogens that are on the double bond, A has more hydrogen, which means less substituted.
Okay, so you're going for B.
Yeah.
Because B is the
More so.
more substituted. But why are you going for the more substituted one?
Because H minus is a small non-sterically hindered base,
So it's going to act like
and H2 minus.
NH2 minus. It's small. It can get to either A or B equally. And so if it can get to either one equally, then the major product is going to be the more stable one. And if you're into reaction coordinate diagrams, what that means is that the transition state for forming the transition state for A and B are about the same. So what's really going to drive the reaction is the stability of the product. That's what's really driving the reaction. Which is probably misstated, but it can get to either one. Okay, so I'll agree with that that's B. So when I wrote this, or the examples I may have given for sodium borohydride in the video, was to have the H minus do an SN2 reaction. But the problem is it can't do SN2 if it's tertiary. So in that case, it would do E2. But you don't have to go back and change the practice problems because I'll accept either answer on the practice problems that are due for today. Vinny? So B is more stable because it's more substituted. So how many alkyl groups are attached to B? There's 1, 2, 3. And again, if you don't like that, put a hydrogen in. Since there's 4 things attached, if one of them's a hydrogen, that means 3 alkyl groups. For A, it's got 2 hydrogens, which means it's got 2. It's got 2 hydrogens, which means it has 2 alkyl groups. So more stable, more alkyl groups, more stable. Okay, so that's what the sodium borohydride would do with a tosylate. We just have to remember it's H minus, and so it's going to react as H minus would. First, potentially as SN2. If that's not possible, E2. But again, I'll accept either answer for today. What else?
For problem F, does it go under SNC mechanism? Or
Problem F. That's gonna. So problem F is where we're taking an alcohol and we're reacting it with HCl. So we have a chiral alcohol, and I've got a CH3 group here and an OH group there. Now the reason that the CH3 group is chiral is so that I know what happened to the OH. Or I know what happens when I react with HBr. Or HCl. So if I react this with HCl, it's going to undergo SN1. So that means it's going to protonate. That means I'm going to protonate the OH to form an oxonium ion. Then because it's a secondary carbon that's attached to it, I'm going to lose the water and end up with a plus charge. And now for the Cl minus, how is it going to add to the ring? Well, it can add 50% above, 50% below. And so I'm going to end up then with 50% bold CO and 50% dash CO. Right, we know, and that's just simply because the overall mechanism is SN1. And SN1 just means that there's a carbocation intermediate somewhere along the way.
Why would it add why would it be both cis and trans conditions?
Because when you form a carbocation in SN1, the carbocation looks like this. Where'd it go? Because when I have this carbocation, it's going to basically look like this. The carbocation is going to be sp2 hybridized. And so that means that the Cl minus can add from this lobe or it can add from that lobe. And there's nothing stopping it either way. So it's going to do 50-50. When it does 50-50 then, that means that half the time it's above the plane, or it's above the ring, and half the time it's below the ring. So it's really not that it's adding cis and trans, it's ending up cis or trans. But it's adding above and below the plane of the ring because I formed a carbocation. Brian?
So even with chloride, it still goes through an intermediate?
Yeah, the zinc chloride is there. I'm assuming at some point I talked about how you can determine a primary, secondary, and tertiary alcohol by visual methods. So, for instance, if you have a primary alcohol or a secondary alcohol, those will react with chromium trioxide, and so the orange chromium 6 becomes green chromium 3, so that you know the molecule underwent oxidation. But if it was tertiary, then it would have no reaction. And then the confirmatory test of that is to take an alcohol and react it with HCl. The zinc chloride is just there as a catalyst to make the reaction go. So zinc chloride plus HCl plus a tertiary alcohol, immediate reaction, 2 layers. Secondary 10 minutes, primary never, unless you heat it, right? So that's where the zinc chloride came from. And those, one of them is called the Lucas test, which is the Lucas reagent, which is, I think, chromium trioxide and sulfuric acid. So those tests, if you, this is where spectroscopy comes in the lab. If you were given a molecule, I don't know, well, at least 30 years ago, because in our organic lab, when I took it, we got 4 test tubes of stuff, and we had half a semester to figure them out. And that took a little more than 4 hours a week. So you would have to go in and ask the secretary for the key to get into the lab all the time because you had to figure them out. And 4 hours a week wasn't enough. It was frustrating. Sometimes they worked, sometimes they didn't. And you couldn't really ask anybody because there was nobody to ask, and they would just look at you and say, get away. Which I should start taking more, I should start doing more of. But so we had an NMR, but we didn't know how to use it. So we had to do all these tests to figure out what the structures were. And so that's what we would do. If we thought we had an alcohol, we'd put it with sodium metal, it would fizz less violently than water would fizz if you added sodium metal to water. So you know you had an alcohol, then you got to figure out is it primary, secondary, tertiary. You would do these tests, and then it would tell you what kind you had. And then you'd have to go on from there. Nowadays, I would take an IR, see my big OH peak, know I got an alcohol in like 10 seconds, and then I'd take an NMR of it, and I'd be able to figure out whether it's primary, secondary, or tertiary relatively easily. So we don't do qualitative analysis anymore, but we did. Right? Okay.
Is the zinc chloride needed in both secondary?
No, I don't even know why I put it in there, but I just kind of put it in there as a, as kind of the catalyst. So it doesn't have to be there.
But in tertiary?
It doesn't have to be there at all. We just know tertiaries and secondaries will react, right, with HCl. Primary, we react with HCl, but we're going to need heat. So on paper, you would react the HCl with the alcohol and replace the OH with the chloride. If I went to do it in the lab, will it happen immediately? Will I need some heat? That's where we get into those details. But the mechanism for tertiary, secondary, SN1, for primary, SN2. So,
is that also going to be products like would it be 50/50 or is it 50 from RN?
well, so when you add PBr3 or you add SOCl2, the advantages of those reagents are that they react with everything relatively quickly. But there's some controversy as to whether or not they retain or invert the configuration. So I don't know what I said in the video. What did I say in the video regarding SOCl2? Well, there's no rearrangements. That's true. So PBr3 and SOCl2 will not undergo rearrangement the way HCl will. But what is it, retention? So I said that SOCl2 would undergo retention of configuration, and then PBr3 does what? That's probably inversion. But when I looked it up on masteringchemistry.org or com, it's free. It's not behind a paywall. They said, I think that, well, they said there was controversy in textbooks. Some textbooks say inversion, some retention, and I think they had them both as inversion. At this point, I'm not going to worry about whether they undergo inversion or retention because of the difference in the different textbooks. Sarah?
So even though you said you don't worry about what's what, why wouldn't SOCl2 be inversion if it's like a backside attack? Or is it not?
Well, all of these reactions are not as simple as they appear.
Oh, okay.
So you asked the question, I'll just show you. Okay, so what will happen with PBr3 is that you'll end up losing an HBr as you add the oxygen to the phosphorus bond. So as you form an OP bond, you're going to lose HBr. And then the question is, then what's going to happen is that this bromine, one of these bromines is going to come down here and then kind of kick off the O and the P because they can form a double bond. And so the question is whether that bromine can stretch from being above the ring through the O, the P, and the bromine can get underneath, and then it would be inversion. Or if the bromine can't stretch that far, then it's going to add and you're going to end up with retention for that mechanism. So that's the question there. And then you could imagine the sulfur being the same thing. So we're not really going to get into that, but here's what I will say. I don't care if you say whether it's it'll be Cl or Cl that way. And you can, I guess you can remember these. PBr3 inversion, SOCl2 retention. But you will get one or the other. You will not get 50-50 both, is the critical part. So in this case, if SOCl2 is retention, that would be the major product. And then for PBr3, the bold OH becomes a dashed Br because that's the inversion. So PBr3 will give you inversion, SOCl2 will give you retention, and if you miss those two, just make sure you give me one product and not both. Vinny?
Are there more reagents like this too that we should be aware of?
There's a whole collection of phosphorus. So there's PBr3, PBr5, there's PCl3, PCl5, there's SOCl2, that's the favorite reagent for turning an OH into a Cl. But there's also an SOBr2 that you could use. They all are going to require the addition of pyridine if you really did them. But, I mean, this is the basic two that I would remember. The SOCl2 in particular, because you were asked a question in one of the quizzes that I haven't graded yet because it was an essay question on you can turn a carboxylic acid into a carboxylic acid chloride, and then if you react carboxylic acid chloride with an alcohol, you get 100% formation of the ester. Whereas if you just add the carboxylic acid and the alcohol directly with acid as the catalyst, you get an equilibrium. Right, that was an essay question. So the way we commonly turn the carboxylic acid into the acid chloride is SOCl2. So that's why that one's important. But all these reagents have one function: to turn an OH into a Cl or a Br. That's their goal. So if you get the inverse and the retention mixed up, I'll give you credit for that. But the critical part is with PBr3 or SOCl2, you get only one product. With HCl, because of the mechanism we wrote on the last page, you're going to get 50-50.
HCl or HCl, why wouldn't it react like that since you mechanism? Because like the Cl minus could just attack that carbon and then the water could be released in that way.
Which reagent do you want to use?
HCl.
With this?
Yeah.
Yeah, when you want to do HCl with that one, it would have been what I wrote down here and it disappeared. What I wrote at the bottom of the page.
Yeah, I mean, I have that, but I'm saying why wouldn't Cl minus just attack that carbon and act like that?
This one?
Why does the water?
Oh. So, okay, so if I gave you the whole collection, I like to do this because it saves time for me. I like to give you all of these different arrows of all the different reagents that you can use. And so, no, you'll see them on the old exams. Well, I think you've already seen them from last semester if you had me. But one of those I might say Cl minus. And what would you write on the other side of the arrow? You want to substitute the Cl for the OH?
Yeah.
Can't? What? Yes. So is OH a good leaving group? What do you have to do to it? Well, now you can do more than protonate it, right? You can turn it into a chloride. You can make it tosyl chloride. Right? We have more options now. But up until that point, how do you make the OH leave? Protonate it with H+. So without the H+, the Cl minus can't kick it off. So this would be no reaction. What?
Isn't it just given if you have a Cl minus that you need H+ for it?
No. Because what if I did this? What if I just added NaCl minus? Or last semester, or whenever you took lab, if you were taking the alcohol and you were converting it to the bromide and you added sodium bromide but no sulfuric acid, you got nothing. Although if I remember it was a couple years ago when we didn't add enough sulfuric acid that we got nothing. We solved that problem this year. So that was the perfect example. If you don't add acid to the OH, you're not going to be able to have the chloride kick off the OH. It's not strong. It's not a good enough leaving group. So I wouldn't have normally thought about putting that in there, but who knows? So what we could also do, because at this point, if you're looking at this reaction, taking this molecule, which in the homework, we made a racemic mixture, and it really wasn't racemic, but we made a 50-50 mixture where we added the halogen. We replaced it 50% above, 50% below. We could do inversion or retention by using PBr3 and SOCl2 directly. We know we'll get one of those two. It just depends on what book we look at.
So, when we're working that, do you want us to specify whether it's inversion?
You're going to specify whether it's inversion or retention by whether the product still has a bold or it's become dashed. So if it still has a bold, it's retention. If it has a dash, that's been inverted. And if it's 50-50, you got to show both products. But let's say that I took my alcohol here and I converted it to a tosyl chloride. So I use my tosyl chloride here. To convert the alcohol to a tosylate ester. And now I say, I want to react that with Br minus. Which step? Well, we don't know if it's 50-50. Because that's going to be because I have a card that says what happens with the Br minus in H on the homework. So if we take this and we make it a tosyl chloride and we react it with Br minus, what do we get? A, B, C, or don't know? The don't know being the option if you don't know. Then I can gauge where everybody's at. Well, we've got a 12-14 split between A and B. Then I've got 2 or 3 C's. And 0 don't knows. So everybody knows, apparently. So, another minute. Discuss.
I don't know.
VR is so it's like one switch. It's kind of attached to the backside.
Okay, time to revote. Time to revote. A, B, C should be. I think your finger's in the way, John. There. All right, everybody. It looks like it's now 3:20 B, and somebody doesn't know now. So B has 21 answers. So why did we move to B? So when I turn this into the tosylate ester, what kind of tosylate ester do I have? Primary, secondary, tertiary? Secondary. So how's the what kind of reaction now between tosylate ester and Br minus? SN1, SN2? SN2 because it's a secondary tosylate ester. So that means the bromine is going to come in and add from underneath as it kicks off the tosylate ester so that it will undergo, that center will undergo inversion. So B is the correct answer. So that's another way to do inversion. If you don't know which of the PBr3s and SOCl2s undergo inversion, this definitely undergoes inversion. If it's a secondary alcohol we started with. If it's a tertiary, what would happen? It would do an SN1, which means you get 50-50. Because if there was a methyl group attached to that carbon with the OH, it'd be tertiary. In theory, once I formed the tosylate ester could leave and leave a carbocation behind. Now, that I'm not sure that would necessarily happen, but I know in the next step when the Br minus tried to come in, it would be looking at a tertiary tosylate ester, and it sure isn't going to do SN2. So most likely then the tosylate ester would leave, and I'll get a 50-50. Sarah?
So SN2 is inversion and SN1 is 50-50. How do you know when it's retention other than that?
So the retention ones are all not SN1 or SN2. Like that thing that I showed you with the phosphorus adding to the oxygen. That's what we would actually call an inorganic mechanism, meaning it's not an organic mechanism, which means that's for another class. Since this is organic chemistry, that would probably be for inorganic chemistry, which is next spring, if you want to be a chemistry major.
Could you repeat what inversion was again? You said what is SN1?
SN2 will lead to inversion. SN1 will lead to 50-50. And the retention is what you're going to get with those SOCl2s and PBr3s. Kyle?
Could you go over number 3, the top part?
Number 3, the top part. 3, the top part.
So that's,
3, yeah, that's the last one. I got a card on that. So basically what I'm going to take my OH and what am I reacting it with? PBr3? Okay, so what's the product? Substituted Br for the OH.
Yeah.
Now add magnesium to that. What do I get? What? Grignard. So it's going to be a minus with an MgBr plus. And what am I reacting that with? No, I'm reacting it with Roman numeral number 2. With structure 2. Then H plus H2. Oh. Then H plus H2O. So what was Roman numeral number 2 then? It's this alcohol plus CrO3, right? So what did that make?
Double bonding. Yeah, there you go.
So now if I react these two guys together,
You have to
Yeah, plus change a lot.
so now if I react those two together, what do I get?
Down the wall. Doesn't it make the, doesn't it be on middle?
So what do you want?
Would be ring, ring.
You want a ring, an O, and a ring?
Yeah.
I hear that.
Makes alcohol.
Makes an alcohol. Okay, so ring, OH, and then what's attached to the OH? So what needs to go here? The other ring?
Oh.
So this gets a little tricky in terms of I will see extra things in this molecule, like the first one. So if I needed to, what would I do? Let's see. So there is my cyclohexane ring, and over here's my cyclohexane or cyclopentane ring that came from the Grignard. And then let's see, what else do we have? We've got orange. So here's my carbonyl. So if I'm thinking about my R minus coming in and doing this, which is what it's doing, then here's my OH group, and what was attached to that OH group? The other ring. So the red is the carbon-carbon bond that I formed between the Grignard and the ketone. Okay. And so rings will sometimes cause people problems, but you really want to just kind of break up the molecule that way. Okay, let's see, I've got a question about naming ethers and ring closures and rearrangements. Ring closures and rearrangements are not going to be on the exam, so I will save those for another time. And then how and when to use the peroxy acid reagent. Peroxy acids and an alkene give you an epoxide. And once you have the epoxide, then the question is, how do I open it up? with acidic or basic. Okay. So we can talk about that as review on Wednesday if somebody wants to bring that up. I've got some practice problems here that deal with the last sort of set of reactions, many of which we've seen before. If you want to take these up, I'll just post the answer key. You can practice those. If you want to take a card and write down some questions for Wednesday, usually when I don't get through all the cards, I put the answer to this in the discussion section. And that's what I may do with this.
You said these are just like they're just practice problems that we've been working on.
They're practice problems from today's lecture. Is what they are.
So in D, I don't know if I did this right.